Hello, and welcome back. Today, I want to continue talking about the topic of magnetic hysteresis. Last time, we looked at how this can be reproduced in the circuit simulator, and today, I will be looking at how this can be measured in real life. So, I will be talking about the setup and the mathematics needed to implement this sort of measurement. So, if you're curious, then keep watching. So, first thing to discuss is how the measurement needs to be set up. Now, in the previous episode, when working with the simulator, we measured the current running through the inductor and the voltage drop present on it. And the specific condition that was set was for the inductor to have an internal resistance of 0 ohms. This is all fine for the simulator, but for real life, this exact setup cannot really be achieved. So first off, our real life inductor does have non-negligible series resistance, and based on the construction, part of the magnetic field from the windings will not be going through the magnetic core. So to some extent, we can consider this as leakage inductance, different from the core-related inductance. So the voltage drop on the real inductor is therefore comprised of the voltage that we're interested in, the voltage drop on the ideal core, in series with two parasitics we don't really care about. So in the interest of better accuracy, a better way of performing this measurement is to use a secondary winding to observe the voltage present on the part of the inductor that is coupled to the magnetic core. As long as the secondary side is connected to a large enough impedance, any losses present in the secondary circuit, so from the series parasitic elements, can be neglected. And well, for the current, with or without the various parasitics, the current in the coil of interest is the same. So if we measure it between the signal source and the coil, it should be just fine. So the setup for today will be as follows. I will be using a signal generator, a 1-to-1 transformer, a high impedance voltage measurement on the secondary side, and a current measurement on the primary side. Now this is far too simple. We need to complicate this a bit. So to complete the measurement, we need to apply a few mathematical formulas to the measured electrical values. On the current side, we need to multiply this with a constant based on the number of turns in the coil and the magnetic field length. And on the voltage side, things get a bit more complex because other than the constant bit, so number of turns and area of the core, we also need to perform an integration. This can be done in post-processing, but we can also add an electronic circuit that will do this for us. So we can build an op-amp based integrator. Now, especially if you have an old analog oscilloscope, or you just want to be able to display the graph directly without any extra processing, this integrator bit will be necessary. Before building anything, I decided to check the operation of the circuit in LTspice. So I have the transformer built as described last time. It's built around the parameters of the ferrite T43-50 core, and I have 20 turns specified on the primary, and a turns ratio of 1-to-1. Then I add the signal source, injecting a voltage sine wave through a 50 ohm internal impedance. And finally, to perform the actual measurement, on the primary side I provided a 1 ohm shunt resistor for the current measurement, over which we can perform the current measurement. And then on the secondary side, I have an integrator circuit. Now, from the measured voltage on the shunt resistor, we need to multiply this by the number of turns and divide it by the value of the shunt resistor and the magnetic circuit length to get the final magnetic field strength in amperes per meter. So in the simulation, this can easily be done using the plot window. And then for the secondary measurement, I have the classical integrator circuit with a few observations. So first off, I added in this large value resistor in the feedback path in parallel with the capacitor, just to have a well-defined DC feedback path. So that is why this 10 megohm resistor is here. And another thing, on the non-inverting side, I added an extra resistor of the same value as the one present on the measuring branch. So the idea here is that both of the op-amp's inputs will have some amount of input current, and the voltage drop on the two resistors should be equal, so the error should cancel out. Well, that's the theory anyway. Finally, to get the flux density, you need to divide the output voltage by the core area, number of turns, and multiply by this 0.001, which is the gain of the integrator circuit with the chosen components. Last observation is regarding the exact op-amp to be used. The gain bandwidth of this component needs to be at least 10 times larger than the initial measurement frequency, and having an offset compensation pin is quite important. So that is why I chose the TL061, because it also has the possibility to adjust its offset. Now the last thing, since the main thing that could cause problems is this integrator, I also added in this behavioral voltage source, which is the equivalent of the circuit we just built. So just to be able to compare the results of the ideal integrator with the realistic one. So finally, if we run the circuit, and we plot out the compensated value of the flex density on the y-axis and the field strength on the x-axis, and well, we can compare to our ideal value, we can observe that we are getting the exact same shape. It's just that there is an offset appearing. So this is caused by the way in which a zero-referenced integrated sine wave is not a zero-referenced output anymore. But this can be fixed by providing a bit of AC coupling just to center the measured value. So if I plot the other input's value, so this B2 net, which passes through a DC isolating capacitor, we get almost the exact same graph both with our realistic integrator as well as with the ideal one. So the circuit seems to be working as expected. Now the final thing that we can do is to step the input signal to see the core's behavior when it's not really getting saturated. So for this, the voltage parameter, rather than setting it to a fixed value of 9, let's just comment this, I will be using a .step parameter to provide multiple input values. So if we run the simulation like this, and just plot out the AC coupled results, we get this nice set of shapes. So we can observe how our core is slowly being pushed into saturation, with the final value being the one in which the core actually reaches full saturation. So now, we should have more or less the final circuit that needs to be built. Well, there are a few more additions though. So the board I will be building to perform this measurement has a set of SMA connectors for the various signals. So first of all, on the primary coil side, I have the incoming signal connector connected to the coil, and then this is in series with a 1 ohm shunt resistor, over which we are performing the current measurement. And then on the secondary side, so the secondary coil will be connected to this connector, we have our op-amp based integrator circuit. Now here, we do have a few components extra to what we used in the simulator. So first of all, we have a set of diodes to protect the op-amp's input in case there's any sort of transient event. Then I added an extra trimming potentiometer for offset compensation, so this will be needed to calibrate the input to be zero referenced. And finally, for the input line, I added in an extra trimming potentiometer just to be able to fine-tune the gain of the complete circuit. So I can't really do much about the capacitance of the parallel capacitor, but we can adjust this resistor. So the product of these two components should be a well-defined value. And well, finally, I'm not really using a differential supply, but rather a single one, somewhere in the order of 16 volts. And from this, I'm using a resistor divider to get the halfway point. So this is the reference that all of the circuit uses. And well, finally, I also added in an LED just to indicate that the board is supplied and that everything is working. So from a layout point of view, I'm starting from the left side with the signal injection and the current measurement, and then most of the right side, starting from the J3 connector, is the op-amp based integrator. And this ends on the top side with the voltage output. So all the circuit, except this one line which is not routed, is a single-sided layout. Let's just hope it works. Now, when I started working on this project, I had very limited faith in the outcome. I knew this could be done, I have seen internet people doing it, but I was just not sure of how well the results will actually turn out in my case. What I'm trying to say is that a better setup than this could have been made. Better filtering, better noise isolation, more expandability. But for today, this board will do. So, to finally test this thing, I assembled this setup So I have my signal generator that is driving the board. So I set this to have 1 kHz and the amplitude will play around with. Then the board is also supplied from the power supply to supply the integrator. And then the output is being displayed on the oscilloscope. So I have the current measurement and the voltage measurement. So when we turn everything on, we get a set of sort of sine waves. But the interesting thing, however, happens when we set the oscilloscope into XY mode. So almost every oscilloscope, even the old single channel ones, will have these possibilities. So like this, we get our hysteresis curve. And if we play around with the amplitude of the signal, so if we reduce it, we can clearly see how this is impacted by the applied signal amplitude. So with large signal amplitudes, we clearly see the saturation behavior, so these flat regions at the ends, which disappear when we are applying very small signals. But the important question is, are the values that we are seeing right or wrong? Well, here we have a problem. Most oscilloscopes have very few input scaling possibilities. So most of the options are either powers of 10, so x1, x10, x0.1, and then a few other standardized values. So at least with this device, I cannot set the necessary 2.58 times 10 to the minus something, or 677, which are the rough scaling values that we would need. So to clearly visualize the results, it's best to export the measurement as a CSV file and then do some further processing on the computer. So if I just go back to the normal view, I will set my save type to CSV and then export this file and do some further processing. Now, after taking the various measurements into a spreadsheet, first I started off by declaring our various constants, so the number of turns, the various core constructive characteristics, and the shunt resistance, and finally our test frequency. So this was important to determine how many points are needed to construct one full loop. So from our test frequency, we guessed our test time period, and then this I compared to the normalized time to observe when I need to stop taking data into account. So from this, I got the parameters for one single loop. So taking all of these and plotting them out, in the end looks something like this. So the graph does look as expected, we are getting the right shape. However, the thing that you might observe is that the graph is not really centered. The point of intersection on the top side is at around 0.15, whereas on the bottom it's at around minus 0.25. So there is an offset. And just like we saw in the simulations, this is happening because my probes are DC coupled. But if we would swap to an AC coupled setup, we will now get a very nice and very centered graph. So with this modification, we can also compare the measurement to what the simulator is giving for the exact same setup. And we can observe that even though the correlation is not perfect, there is a very reasonable small difference between the two. So our measurement is not at all off compared to what the simulation is telling us, as long as both of them are scaled to the same degree, of course. Now, I went ahead and scoured through the various data points to find the intersections with the graph, and I plotted everything out in this table. So here we can see our datasheet values, simulated values, and finally the measured values. And the first thing that we can notice is that our remnant flux value and saturation flux are slightly smaller in the simulation compared to the datasheet, which means that we're not really driving the core with enough signal. So that's why these are smaller than the datasheet. So finally, we just need to compare the measured values to the simulated ones. And we can see that the difference is not all that great. So I guess with a bit more attention to the setup, the values can be made to be far more close. Anyway, one of the useful outcomes of this exercise, other than validating the simulation and the core properties, is measuring the core losses. So other than the axis intersections and the extreme values, the other valuable information to come out of such a graph is just what the power dissipation will be on the core when the specific driving signal that is being tested is applied to it. Now this is quite easy in the simulator. You just need to plot out the power dissipation on the inductor. So this can be done by holding the Alt key, going over the inductor, this thermometer appears, and then when you left click, you get the power dissipation being calculated. And then this can be further analyzed by holding the Control key and left clicking on the plotted value, and from here we get our average dissipated power. So with the setup, it's somewhere in the 11 milliwatt region. But performing this calculation is a bit more complicated in real life. So for this, we need to determine the area enclosed by our hysteresis loop. One method that I found for this is applying the shoelace formula. This takes all the points on the graph, so x and y are our coordinates corresponding to the magnetic field strength and magnetic flux density, and you multiply and sum up things, and somehow this works. In the end, this will give us the energy dissipation in joules per cubic meter per hysteresis cycle. So to get from this to average power, we need to multiply this value by the volume of our core and the frequency at which the core is being driven. So this will give us the average power dissipation on our core. So I tried to apply this calculation in our Excel file. So after extracting the BH parameters for a single cycle, so you need to be careful not to calculate the area of multiple hysteresis cycles, but just a single one, then I performed the various calculations, so these parameter multiplications, summed everything up, and finally got the total area at around 19.78 joules per cubic meter. Finally, this was multiplied by the core volume and the operating frequency, and this yielded a total power of around 7.5 milliwatts, which is not that far from the 11 milliwatts from the simulation. And well, it's perfectly normal that our value is smaller, since our loop area is also smaller than the one from the simulation. So I guess that the calculation worked out just fine. So what is the actual utility of such an exercise? Why measure and process the hysteresis graph of a magnetic core if you already have all of the data in the datasheet? Well, all the information in the datasheet is given under very specific test conditions. Conditions which, more often than not, are different from your actual use case. So, testing a core under different user-imposed conditions will yield better information on the final use case, and help in better understanding the behavior of the core in your final product. So, when a high degree of accuracy and in-depth knowledge is needed, performing such a measurement is crucial. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.